So let's keep advancing the Erwin Hauer screen. What I'd like to do with this tutorial is to take what the strategy we've developed in terms of an individual panel that we can see here, where we were using the dimensions of the edges, and we were using kind of taking points along those edges, and then using this to develop the three-dimensional tangent curve, and then a series of patch surfaces that allow us to do this. What I'd like to do now is to take this knowledge from the individual panel and start to look at how this can be panelized across the surface. And while we're at it, let's add an attractor point so that these values could vary across the surface as well. Why not, right? We'll jump right into both of these. So what I'd like to do, if you want to start a new file, you can, a new Rhino file. I'm going to keep this older Grasshopper file open and just work off to the side so that we can see how the individual panel works as a way to build the framework at multiples, across multiple panels. So if you want to get started, what I'd like to do in Rhino is to build a simple lofted surface, maybe not unlike something that might be able to stand. I'm just going to use two curves to do this. Maybe a more extreme curve on the bottom and a simpler curve to be on the top. I'm going to move one of those curves up and loft between the two. And when I loft between the two, the setting that I have is to rebuild with control points. In this instance, I'm not trying to match exactly the curves that I drew, but instead I want to get a kind of more uniform surface that's generated with the loft. And so I'm going to do rebuild with 10 control points and say OK. And the last thing I'll do in Rhino is to add a point. We'll use this point as an attractor point. So to get started in Grasshopper, let's grab both of these things. So I'm going to create a brep container. And let's set one brep, which is our lofted surface. And while we're here, let's create one point container, which will be our attractor point. Okay, so working with both of these, the first thing that I'd like to do is to isotrim the surface into a series of panels. So let's see what we need with isotrim. We're going to need a surface and a domain. So let's add our brep to that. And for the domain, let's use divide domain, which will be both our domain will be our brep, and then let's look at a series of U and V panels that are maybe 5 is less than 50. I'll copy this and let's plug this into U and V. Sometimes it can work where you can use the same, but because our lofted surface is longer than it is tall, I want to be able to change those. So I'm going to hide the preview for the brep. I'll actually hide the preview of the lofted surface, and now we can see our ISO trims, which are 5 by 5. I'm going to work. We can see U is the height, and V is along the length. I want to get these, we see as we increase or decrease, I want to get them to be somewhat uniform, somewhat square. We don't need a ton of divisions right now, but enough for us to kind of see the benefits of working with multiples. So we've got our iso-trimmed surface. Now what I'd like to do is to deconstruct that B-rep, which will give us access to the individual faces that are here, as well as the edges and the corner vertices. So we see we get faces, edges, and vertices. As we do that, we can always hide our iso-trim surface. And what's also nice with this, given these faces, I can get the centroid of each. And so now we see that we've also got the center points of each of these panels. I'm going to use the centroid as a way to locate a length as the kind of center of the panel from our attractor point. And eventually we're not going to use this for specific geometry, but we are going to use it as a kind of point to measure from for each of the panels. So now that we've got that, and what I want to do is just do a kind of proof of concept of the attractor point and make sure this is working, and then we'll add our kind of framework system or edges and dividers for the individual panels for the Erwin Hauer panel. So let's now locate our attractor point in relationship to our surface. We could find a dimension from these, but I do want to use the surface closest point. And so we can plug in this point, and let's use the B-rep for that. And now we can see that this point shows up in relationship to our attractor point. I'm just going to move it up. And so now we can see that this also works in 3 dimensions. So our attractor point, no matter where it is going to find a point on the surface. Once we have that, we can draw a series of lines using the endpoints. So our start point, let's use as our attractor point that's on the surface, and our endpoint, let's use our centroids. So now we can see that as we move our attractor point, we have a series of lines that are created from the centroid to a point on the surface. And what we're not getting the dimension actually along the surface. That's a much more complicated dimension to get, but basically the straight distance from that point. So what do we get when this happens? With those lines, we can capture the length of each of the lines. So let's connect this, and let's look at the panel and see what we have. So 180 inches, 40 inches, kind of in that range. What's nice about having these lengths is that we can begin to map this to something that we'll use for the Hauer panel. So let's find the min and the max from this list of dimensions, and for that I'm going to use bounds. I want to flatten the list, and it will give us a domain. And then we can also deconstruct that domain. So that domain, as we pull this from the bounds, is 5 to 197. We plug this in. Now we get the individual, the min, and the max. So as the attractor point moves, these dimensions will also change. All of the dimensions will change, as well as the min and the max. And the reason why I'm doing this is that I then want to take these dimensions and I want to remap them to a set of dimensions or parameters or even percentages that we can use related to our edges in the way that we are controlling the panel. So let's look at remap numbers. And what we'll do is we're going to take that domain, which is our source, right, the min and the max, plug that into the source. We're going to plug in our lengths into the values, but we want to flatten that so we just have that straight list. And then I want to have a target, which is going to be another domain. So let's construct a domain. And without kind of remembering off the top of my head what those percentages are, let's just use a panel and make, let's say, 0.02. To 0.4. We can set these as the min and the max of that domain. Plug it into here. And now let's get another panel and see what we get out from the remapped numbers. So between, let's make this a little more extreme. So 204 is maybe not our max, but close to it. And now here we get a 0.366. We come down, some smaller numbers here, 79 maps to roughly 0.14. We can work iteratively with these mapped numbers, but we're going to use them now first as a proof of concept to, let's create some circles. And I want to make a series of circles as a way so we can see exactly how this works in terms of the remapping across this surface. And then we'll go into using the developing the Erwin Hauer examples. So let's pull our centroids in to a surface closest point. So the centroid will be the point. Our surfaces will be the faces. And now we can see we get these points as they're highlighted on here. And now let's evaluate surface. And the reason why I want to evaluate surface is that we can get the normals from this in relationship to or creating a frame or doing other things with this. So remember, we have to, even though it asks for point here, it's asking for a UV point. So we can pull in this UV point. Now we can see we get a series of planes across the surface. Let's make a circle using the center, the normal, and the radius. So the center for us will be the points. The normal will come from the evaluate surface. And now what I want to do is use the radius. All of those are consistent. I can hide a couple of these things. Maybe we can even, well, I'm going to leave the lines here from the attractor point so we can see exactly what's happening. But what I want to do is map the radius from the mapped numbers to the radius of the circle. And I think if we just do this, they're going to be incredibly small, and we're not even going to see them, and we're going to see a whole bunch of them. So what we want to do, I believe, is flatten down the center and the radius. And then I also want to add a multiplier here as we look at this, coming from the mapped values. So let's do a multiplication. Not that one. And so let's multiply our mapped values to something that's, let's say, 1 is less than 25. So we can really exaggerate these if we want. And now we'll plug these in for the radius values. So as we go from 1, okay, we're starting to see these grow. And so when I highlight the circles now, maybe I'll hide a few other things. We can hide our lines, centroid, and our faces and edges. Okay. So with that, what we have is, as we move our attractor point, we can see the circles are getting smaller because they're very close, and they're getting larger at the other side. We can use the multiply to vary these slightly. The other thing that we can do is that if we actually want the aperture to be larger, we can flip-flop the min and the max of this domain for the target. So let's do that. Now we can see that the closest to the attractor point, the apertures, or these circles that are on the surface, are the largest. So that gives us a little bit of control later to understand that. This gives us a little bit of control, or the circle, putting these circles in the short term gives us a little bit of understanding about how these are going to work. So what I'm going to do is I'm going to group the circle. We don't need it anymore. We can just leave that floating out there. We are going to come back and we'll grab those mapped values later. So let's hide our circles. And now let's think about how we were working previously with the Erwin Hauer screen. And what's nice is that all of the work that we did before, you can kind of connect into this. If you want to do it, if you want to start over, you can. And I just want to show you, kind of start with that idea. Let's start with these edges or even with the diagonals, right? And so what we were doing is we were grabbing percentages as a percentage along the length of the side and starting to create these edges and points that we could use for the tangent curve. So to start with that, let's see what we can access and how we can access these different edges. So we have the edges from the isotrim, and let's pull a list item from those edges into a list, and let's see, let's make a slider 0 is less than 10. And so what's happening is that we're getting all of the edges. Let's look, let me just start with faces. Let's flatten it down. Okay, so first, second, third. So we need a few more. Let's go to 50. So we can see the way all of the panels are in order, going at least on mine from left to right, bottom to top. So that's good to understand. Now let's pull in rather than the faces, I want to work with the edges. So these are a little bit, looks like the same thing working across and then up. But I don't want, actually let's look at the structure or the panel. So we're getting one planar curve. And that's probably because we're flattening it down. Let's see what happens if we get rid of that. So now we're getting, looks like the panels or the edges as they move across. So my speculation is a little bit that we have 4, then another 4, then another 4. And maybe let's even just look at those edges, bring them into the panel. Okay, so we have 0 through 3, which gives us 4 edges for each of those faces. Let's do this. Let's zoom into our list item and we can add, so we have 4 individual outputs. And let's add a curve container for each one. And connect these. So let's start with maybe the diagonals. The way that we did that previously is we used evaluate curve. Our curves will be here. And so let's reparameterize these. And I want to reparameterize it before I copy it. And let's see, I can also give it a parameter. So the way that we did this in the previous tutorial is we had a slider. And let's just say that 0 is less than 1.00. And we'll plug that in. And let's copy, I think we had 8 of these before. We'll just space them out. Okay. And 1, 2, 3, 4. Separate them slightly. So now let's plug in each of, well, we shouldn't have, we're going to do a slightly different parameter for there, but let's plug in the curve to the top 4 of these, and let's see what happens. And this is really where it gets pretty interesting. So we can move these points along. If I zoom in, right, we're starting here on the first one. This is 1/4 up. This one's 1/4 over. This is 1/4 down, and this is 1/4 over. We just have to be careful because the 1/4 over is also what we're seeing over here. And so we're just going to end up getting these to be kind of overlapping with one another. The other thing that we want to do, if you remember from the previous tutorial, is we're going to do a subtraction. And we're going to subtract from 1. And so whatever parameter we have here from our slider, and we subtract from 1, we'll plug this into our parameter down here. Plug our edges in here. And now as we move our slider, we'll begin to get, and as we move from 0 and approach 50%, those points are then in a crossover, and then come across the other way. So this is working, and I'm going to just dial this down a little bit, and let's build a couple of lines. I want to do the diagonal lines first, then we'll use the attractor point as a way to vary those. So we're going to use a line with endpoints, and let's see, I think we're also going to need 4 of these. And so let's take a look at our first panel. Let's start with knowing that they're moving clockwise around here. We'll start with this first lower point. That'll be our start. Our end is going to be our, and you'll see what happens if we select one or the other. It'll either end up coming across or up. Let's look for, I believe it's this point. Let's give it a try as the end point. And see, this is actually the point that's coming across the 1 minus. So we'll continue to go through. That should be this one, will be our end point. Now we have our first diagonal. Let's look for our second diagonal here. This should be a 1 minus. That'll be our start point. Now we're looking for this, which should be above, which is, remember, coming clockwise across, should be our third one. Now we'll come kind of diagonal and down. So let's look for, this should be our second one up from the top. And we're going to come to a 1 minus, our third 1 minus. And then let's come from our first 1 minus. And that will go to our fourth. There. So now we have those diagonals across all of our panels. These diagonals that we just drew within Grasshopper represent the diagonal lines that we see here that are flat before we kind of elevated or added thickness to pushing these off with our interpolate curve. Right, so I just want to get you to the point where we are doing this at a scale of multiples across the entire surface. At this point, we can hide those points. The remaining point on here is our attractor point, but remember, nothing's happening yet because what we have to do is change our slider to be our mapped values from these above. So let's give it a try. It's going to be easier to plug it into our subtraction, where that will take care of 4 of those. Really what we want to do is, let's see, so we need our mapped values, I believe, to be grafted. Okay, there we are. So by grafting the map values, these are dropping in and working appropriately. Let's just also plug the mapped values into the parameters for the top 4 evaluate curves. We no longer need the slider. And so now we can see coming across that surface, it may be a little too extreme where it gets very large, but if we move our attractor point, we can see further away from the attractor points, the cross members will be very thin. As it gets to the middle, they're going to be very thick. If it's too thick, let's change our domain value. Let's try 0.3. That might be a little bit better in terms of how wide that element is. And if it's too thick, we can always dial this down. And remember, if we want to have the attractor point have the aperture smaller, we can just flip those values. And so now close to the attractor point, very, very thin panels. Far away from the attractor point, thick panels. So with this, you should have an approach, right? We've built the panels individually, two-dimensionally. We built the panels individually, three-dimensionally. Now you've got the framework to keep building off of these. Where we are here is where we were at an early stage in building the panel. If you continue to work with these in the same way that we're working here, you'll get a range of variable Erwin Hauer panels across this entire surface. I don't want this tutorial to be too long. I know this is pretty long as far as tutorials go, but taking you through the process and allowing you to see how to go individually, two-dimensionally, individual panel, three-dimensionally, now being able to control this kind of framework and get variability of those panels across the entire thing. So give it a try, and I'm happy to answer any questions that you have or any problems that you run into along the way. But now you should have an approach of using the attractor point, using the isotrimmed surfaces, and remapping the numbers to produce that variability. Again, let me know if you have any questions. Thanks.